Welcome everyone. Today I'm presenting a research seminar. The title of the presentation is an integrated approach to price differentiation inventory decision with demand leakage, and my name is Syed Raza and I'm the presenter for this presentation. Uh, we briefly start with our agenda for the today's presentation. We start with the introductions, we discuss some background towards the problem development, and then we define the problem, we develop the models for the problem and analyze them and develop a numerical experimentation and report some conclusions and future works. Well, in terms of the definition, the background of the problem, the research is presented in here is pretty much related to the revenue management, which is one of the closely related fields to the supply chain management. But in general, it's a science of maximizing profit through market demand forecasting and the mathematical optimization of pricing and inventory. But there are several other definitions beyond this. One such definition is available from Informs, the use of data, mathematics, and computer to understand to better understand the purchasing behavior and to recommend better prices. So revenue management is more related to pricing and inventory decision management to maximize the profit. So this way we can conclude. In general, the revenue management has a lot of applications similar to supply chain management studies. Most effective areas could be airline, which has been using the revenue management for over 40 years, cruise lines, hotels, cargos, car rentals, restaurant, broadcast, which is advertisements, and manufacturing sector, which start to getting up in terms of doing profitability analysis. Obviously, the revenue management has been most widely practiced in airline industry, which has over 4 decades of use of OR techniques for maximizing the profits for airline industries. In general, when we model the problem, we need some background. For example, if this is the deterministic demand price relationship, if I set the price, then the demand I experience would be this, and hence this area would be my revenue, right? But these surplus demands which I could not capture because of I'm setting only one price. This problem become much more complex if I have a stochastic demand, and the analysis would be different that we will discuss. But when it comes to problem of our discussion of today's presentation, we have a very simple and widely noticed problem. The problem is this, that a firm has products to be offered, and these products could be the same product or different products. These products, if same, then they could be offered from using different distribution channels such as online versus physical sales. You may have noticed that Amazon and many other airline industry, they sell their products online, and they also have offices to sell their products. So in that case, what happens is the market contains two particular segments, and depending on the purchasing behavior, these segments could be widely observed. What happens that a firm might price or sell a product in a market segment which is willing to pay more price, and hence it will pay at the higher price, which is the P1 for instance. But on the other hand, a firm may choose to sell the product, which is the same product, a different product, into a secondary market and at a price of P2. Now here's the case that there are obviously the heterogeneity among the customers, and not all customers are the same. Some could be more informed, some could be less informed, and in that case, the person who could easily get an access to, say, go to Barnes and Nobles and Chapters and the other bookstores, study the book and take the information from the help desk there in the book. But when it goes to purchase, he goes online and purchase from Amazon, which cost him less. So in that case, these type of things basically cause a cannibalization effects in the market, and they are always there. So this is the our core concept. The concept is that a firm is offering two products in two different market channels, or maybe two products in different markets, and they like to see that how products can cannibalize the customers' demand, and in that case, what should be the optimal strategy for the firm. This is a very simplistic analysis that we presented here. If the demand is deterministic, in that case we have a price called differentiation price. A firm may set a price that any price less than this price is a discounted price, which is sold in the market segment 2. Any price greater than this price is the full price, which is sold in the upper market segment. Proposed research, obviously, as we discussed in here, that discusses the profitability of the firm. It offers a product at a differentiation price to segment its market demand into distinct market. So not only the problem of setting the prices, but also setting the market price differentiation. We develop mathematical models for a firm which enables an integrated framework to exercise pricing and order quantity decisions, which is the inventory, and the market segmentation, which using the price differentiation. While it experiences an imperfect segmentation because of the cannibalization, it results demand leakage. And obviously, the objective would be to determine the pricing inventory decisions with the differentiation values. Now, obviously, the first way of addressing the problem is to see if there is no risk in the model or no risk in the market, as if the demand in the market deterministic. And if this is the case, then how to develop a model in such a situation. So we believe that the product costs some value, and the product is sold at two prices at two different markets, but the market experiences the demand leakage. So basically the theta is the percentage of leakage, which is fixed parameter in this case, that is leak from the full price market segment demand, which is U1, to the discounted price market segment, which is the Y2, which is the demand that is realized by the firm in the second market segment. And we may notice that the leftover, the price, is giving you the remaining demand segment that you can get from the setting the price to. Now we continue on this, and we assume that it's no longer the risk less analysis or deterministic analysis, but rather we like to see what if the firm's behavior is experiencing to be the stochastic demand, and hence we believe that demand having a additive model, which is most widely used in literature for deterministic demand plus the stochastic random parameter, which is independent of the demand, and this is in the case of both market segments. Now here are certain notations that we have developed. We have a cost of the product, we have the demand leakage factors, we have the maximum market demand, we have price sensitivity, and we have the holding and shortages cost, and we have certain other parameters that we have decided, which are auxiliary, and then we have decision, which are prices and differentiation price and the quantities. So we continue on, and using those notation, we built a model for the firms who is segmenting the market into two market segments using differentiation price. As we can notice here that this is the price and this is the order quantity, and this is the stochastic demand. So it's typically a Nussbaum problem with pricing, which is commonly used in many of the modeling for supply chain, studying the contracts and interaction between the retailers and manufacturer. So this is one of the typical scenarios that we have used in here. These are the holding and the shortage cost and the cost of purchase. And this is a linear constraint, which basically asks that the differentiation price is something that differentiates the two markets, and the price of the full market segment, full price market segment is P1, and the price for the discounted market products or the segment is P2. And these are linear constraints. So typically we can notice that it's a nonlinear program subject to linear constraints. We skip some analysis in here, but we have a paper that we would like to share, and in this paper we deducted at how the transformation could be reached to this, which is a revenue from the price, shortage, loss from the sales, and then this is the loss due to the uncertainty in the demand in the market and subject to the same constraint. There are two ways of analyzing this nonlinear program, which is stochastic in nature, subject to linear constraints, is to follow a sequential optimization procedure or a joint optimization procedure. In the sequential optimization procedure, most of the time the firms work like this way, that they decide on a parameter, and then based on a particular decision on a parameter, they decide the other control parameter. For instance, here they may decide the price first, and then later on they decide on the quantity or the inventory decisions given the prices are known. So first prices are optimized and then the inventory decisions are optimized. But in here, the two decisions are taken jointly. The advantage of sequential optimization that it can give some closed form solution to us. So let's see that if we deterministic problem, we ignore all the losses that are happening due to the shortage in the holdings and because demand uncertainty, and this is the deterministic problem. So it's a deterministic problem subject to linear constraint. As we can see that we can use Karush-Kuhn-Tucker optimality condition to obtain some results, and we are reporting some results that optimal prices are determined by solving these following two typically linear equations, and where the prices, the demand values are these. But one special situation is that a firm is selling the same product into different market using distribution channels. So in this case, we can reduce the cost to a single cost, and this further reduces to a very closed form solution for determining the price. Notice that the optimal differentiation price is at the price for the right market segment. While the decision has been taken for the prices, somebody could take those decisions for any given price which has been taken before. You can optimize the order quantities, which is in this situation is stochastic. And we optimize this using first order optimality condition, and if we explore the revenue function for a given set of quantities, we found that it's jointly concave in the order quantities. Now we continue for the stochastic problem, and this time we basically look into the problem jointly, meaning that we are trying to find out the solutions for the prices and the inventory decision and the price differentiation for the market segmentation jointly. So in this case, obviously we lost the ability to get the closed form solution. So these are the two nonlinear equations to be solved, which can be linearized given we assume for instance some cases such as uniform distribution, and we can get the optimal order quantities, and the two decisions are usually determined numerically, and the optimal price differentiation for the market segmentation is at the price for the full market segment. A very interesting situation that we can explore for this stochastic problem is that a firm may not know the demand behaviors, and which is quite popular and quite obviously noticed in many market situations, such as when somebody launches new product, somebody basically goes to the new market segment. So these are the all situations where the demand distribution may not be known, and hence a use of scarf rule, which has been later studied in Guligo and Moon, which is commonly known as distribution free approach, is most widely and very obvious solution for the case where the distribution of the demand is unknown. So use of demand distribution basically transforms the problem, and this is how we transform the problem. So this is the stochastic problem, and basically it builds a lower bound on the problem that this particular parameter, which has been noticed in here, is transformed into a lower bound. So this is a lower bound. You can see the delta, meaning that it's a lower bound on the problem. Now if we study the problem, so we can find that using the first optimal condition for a given price, the order quantities are optimal order quantities are these, which are, and this is the critical fractile, which is commonly used in literature for the Nussbaum problems and the problems in supply chain management and inventory decisions. But the other thing that we can find out is this lower bound, the revenue function in the lower bound is jointly concave in order quantities, and we can also notice that the bounds or the deterministic revenue minus the lower bound on the revenue is at most up to this value, which is very vital information, because no matter how good or bad the market behaves, the lowest possible revenue cannot go beyond this. And using this particular definition, we can build a new transformation, which we can say the new distribution free problem, df prime, and in this case the other terms which are complex are reduced by this lower bound. Now we can analyze this non-linear program again subject to linear constraints using the Karush-Kuhn-Tucker optimality condition. We found that the optimal prices are determined, and optimal prices can be obtained as the closed form. Notice here that the price for the deterministic, for the case of distribution free, is always lower than the deterministic when the problem is basically riskless, meaning that the demands are deterministic. and it will depend many factors, but one such factor is the market variability. Here we also assume that for simplicity of analysis to get the closed form that the two costs are same, but also the two markets, they have similar market variability. Then we continue on a numerical experimentation. In our experimentation, we conducted the research, we extended the research that was earlier reported in Phillips, one of the well-known books for the revenue management, and we collected some of the parameters from the book to validate the model. So we took the parameters from there, and then we have taken the cost and the market share and the price sensitivity, these parameters, and we tested our model for the normal, uniform, and normal distributions. So here is the result for the normal distribution. We consider different demand variabilities, we consider different demand leakages, we consider that if the firm chooses not to segment the market, what is the optimal revenue that you can achieve by solving a single period New Zealand problem, either analytically or numerically. And then you can consider that if you do sequential optimization, meaning you solve for price first and the quantities after, you're gonna get this revenues. And this is the joint optimization. You can see that the joint optimization yields slightly more revenue. That's very ignorable. But here the advantage of sequential optimization is that you can get a closed form solution, and this is much easier at a firm level to be implemented. You can see as the demand variability increases, the revenue drops, and of course the prices do increase. And similarly, as the demand leakage increases, the firm starts to allocate more for the lower market segment, because the more and more customers are leaking to the lower market segment. Similar trends are being observed for the uniform distribution case. Only thing that we noticed that the revenues are slightly lower because the uniform distribution is more wider and more imprecise compared to the normal distribution. So this is one of the rationale for having a bit lower revenue compared to the uniform distribution case. We studied this particular graph, and we plotted this. Actually, the purpose of this, that this is the revenue for a single market segment, and this is the revenue if the firm does not optimize the differentiation price and uses a arbitrary differentiation price of 7. So in this case, the firm is only good to segment the market if the demand leakage is up to, say, about 12%. But if the proposed strategy that we give in the paper, if they use, then the firm would always be above the threshold of the singles market segment, even if these demand leakages are higher. So this gives a motivation for a firm to use the proposed model when it comes to the market segmentation decisions and pricing. Similarly, we found that the impact of differentiation price, if the differentiation price is higher, the revenues are relatively higher, which makes sense because a firm is giving differentiation higher, meaning that already segmented the market for lower market more than the upper market. So this is what makes the sense in here. We did the analysis for the distribution free approach, where the demand distribution is unknown, and hence we computed the results for the price and the quantities. Here we can notice that a firm might price lower and allocates more compared to when the distribution of the demand is known. But one important thing is that there is a parameter which is used for the performance measurement of distribution free approach called expected value for additional information, EVAI. And as you can see that this is the revenue gain the firm would obtain if the demand distribution is known to the firm. So if the demand distribution is known to the firm and it uses the distribution free control parameters, this is the maximum gain it can get for the case where it does not know the distribution. So knowing distribution may not make a lot of sense in here, but there is a catch in here that because we use linear demands, we use the additive model, so this is the case that the performance of the distribution free approach is very good. Summary of the results in here, that the research developed for firm and integrated methods or integrated framework is presented for market segmentation that uses differentiation price to segment market, pricing, and inventory decisions, which are done jointly. We develop innovative mathematical model, basically rooted into a New Zealander problem. and then we developed the numerical experimentation. We borrowed the data from numerical published research, and we experimented our models. We found that the proposed mathematical modeling approach gives substantial revenue gain, especially when it comes to the comparing the price differentiation effects. In many cases, the revenue are could be lower if the firm does not choose a optimal price differentiation strategy to segment the market, as we have seen in some of the plots. This paper was published, actually the research has been published in International Journal of Production Economics as an integrated approach to price differentiation, inventory decision with demand leakage. This research has been extended because this paper was published from a funded research. So we extended the funded project into different directions and we were able to get some research done, such as we did a risk tolerance analysis looking at different objectives for a firm, which is risk averse, risk neutral, and risk seeking firms. Then we also had some integrated approach for greening decisions. For example, a firm is choosing to green the market, and hence the market launches two products, one is green and one is regular. And if that is the case, then what should be the pricing and inventory decisions? We also integrate for a firm's pricing decisions with the production decision in a process targeting setting, which is a firm is producing products such as beverages and others, where the quality of the product is determined through the mean fill or the mean amount of the content in particular product. Well, coming back to my research interest, a wide variety of interests that I can be able to teach and serve: operations management, services operations management, which is basically revenue management, management science, inventory management, business statistics, business analytics, revenue management, courses related to supply chain, project management, courses in production planning, control, statistical modeling, which I've seen, and some of the stochastic process is for business application. This is not the complete list, but I looked at the course content of the university, and I found that these courses are being offered in a different course code. So I looked at this and I found that I'm quite confident in offering those courses. I'm also willing to develop some excuse me, some new content such as revenue management pricing, which has been sometimes my area of research in my dissertation. I would be very interested to collaborate with faculty and develop business analytics programs. Game theory is one of the areas that I can definitely would like to bring some aspects from game theoretic perspective with the application of the microeconomics and OM, operations management. And my background in meta heuristics and intelligent method of optimization gives me also an opportunity to create something called artificial intelligence with business application, which is currently quite known as data science. So this is the pretty much my contributions towards teaching. When it comes to research, I've been working in research and I've worked quite a bit for different topics. So in that case, I would be very interested in collaborating with faculties to have some joint contribution, play as a team member. My research interests are here, but not limited to these. We can also develop some new areas of interest. So revenue management, of course, pricing, supply chain management, business analytics, business simulations, stochastic processes, production planning control, and advanced optimization methods such as the meta heuristics and the others. So this is the case. About myself, I received some research awards as well, such as Emerald Literati Network Award in 2016 for a paper that I published in Journal of Modeling and Management. I received the Best Researcher Award in College of Business in Qatar University 2013. I received the Best Paper Award in 2013 International DSI Conference in Bali. I was rewarded the Young Scientist Research Experience Program Award for $185,000 in 2010. I received NPRP grants totaling $1 million as a lead principal investigator in years 2010, 11, 12. I was also given Best Distinguished Paper Award in 14th Annual DSI Conference in USA in November 2009. My publications are about 40 papers in journals and conferences and books. Some of them are chapters. About 25 papers are forthcoming in international journals, mainly Scopus indexed and higher. Uh, I have published in Journal of Modeling, 2 papers. I have published in International Production Economics, European Journal of Operation Research, uh, Computers and Industry Engineering, Applied Mathematical Modeling, Design Studies, Journal of Heuristics, 4OR, and there are several others management-related journals that I have also published. Most of them are having some impact factor. Most of them they have ABDC ranked, and most of them are also Scopus indexed. So this is a summary about what I have published. I've also been very keen in supervising, mainly because I had funded projects, so I was able to hire RAs to in those projects. So far, I have supervised about 5 to 6 RAs. I've also supervised a PhD student. When I was at Concordia, I also supervised a master student, and I've also supervised 26 applied graduation projects at Qatar University, and one MBA thesis project supervised at HSC Paris, Qatar campus. I take this opportunity to thank the committee for interviewing me and listening to the presentation. If you have any questions, please feel forward. You can pass it on to me. I would be glad to answer. And thank you very much again for listening to the presentation.